Hi all. Today we are going to discuss about bootstrap technique and bootstrap circuits. Before getting into the technique used for bootstrap, we will see why bootstrapping is required, right? Bootstrapping is used for generating a constant current through a capacitor so that the voltage across a capacitor increases linearly. We have our conventional charging mechanisms. If you are applying a V volts through a resistor to a capacitor, if the switch is opened, then capacitor starts charging. If you're assuming initial position of the switch is at closed state, then Vc of t will be 0 initially at time t equal to 0. Vc of t is 0. If you're opening the switch at t equal to 0, at t equal to 0, the capacitor starts charging from 0 volts, and as the capacitor charges towards positive V, the capacitor voltage here increases. But this is at fixed voltage V with respect to a ground or reference. Then the current flowing through the resistance R, that is the charging current of the capacitor when switch is in open position, that current decreases due to an increase in potential at the right side end of your resistor. This is at constant. So you never get an initial slope. The slope decreases further as time goes up. So at t equal to infinity, it will get charged up to V volts. The problem here is it is an exponential curve. Slope is getting decreased as my current is getting decreased while charging up the capacitor. And if you want to make the voltage across a capacitor equal to 0 at next instant, let us say t equal to t1, you can close the switch at t equal to t1 so that Vc of t suddenly becomes 0. Even though you cannot change the capacitor voltage suddenly to another value, we are assuming that the capacitor is ideal, and while closing the switch with a capacitor voltage not equal to 0, will dissipate energy across the switch. And ideally, you can make it to 0. Practically, it is impossible. And we're expecting a sawtooth or sweep waveform that varies linearly with time. And we end up with an exponential curve. And the entire charging circuit can be obtained by using transistor also, in which you need not use an external switch. You can control by applying pulses at the base of the transistor, let us say Q1. Suppose if input is at 0 volts, this will turn off your transistor, right? Capacitor is initially charged, then capacitor charges through RC, but the charging is also exponential because this is fixed and this voltage is at 0 volts initially, then it is increasing. So this charging current will decrease as voltage across the capacitor increases. So here also we'll have an exponential charging. If you want to discharge it completely, capacitor voltage, then you can apply a high pulse at the base that turns off your transistor. Of course, it will take some time to turn off the transistor, So it will come to 0 up to some time. So you are expecting this is t equal to t1 at which I am applying my input signal. So anyway, the charging is not linear, it's exponential. To ensure voltage across the transistor and P and transistor to 0, you have to wait for a fixed time. Ideally, you can say that it will come down quickly. Practically, it will take some time, and you cannot make that output voltage or voltage between collector and emitter or VCE equal to 0. There will be a non-zero value. We'll call it as VCE sat. So it will be at VCE saturation. But the problem is here also the charging is exponential because this charging current depends on capacitor voltage. So capacitor voltage increases, charging current decreases, slope decreases. Right? So if you are able to make a constant current that is flowing through the capacitor, you can generate a linear sweep. From fundamental equation, let us say Q equal to C times V, and this current I is nothing but charge upon time. Q equal to I times T, that's equal to C times V. So if you're observing V, voltage across the capacitor V or VC equal to I times T upon C. That will give you I is constant, C is also constant, then we'll have alpha times T, VC of T. Then that curve is a linear curve, ramp, VC of T and T here, linear curve, alpha T. Alpha is I upon C here. So if you are varying the charging current, you can vary the slope up or down. And you can use an external switch to make the capacitor voltage to 0. Ideally, it will come to 0 quickly. So if you are able to generate a constant current source, you can get a linear curve. And generating a constant current using a PNP transistor is shown here. If you are fixing the base voltage VB here by varying R1 and R2, and if you are selecting the RE resistance properly, you will have a particular VEB that will be in the neighborhood of 0.7, and that VEB exponentially related to the emitter current or the collector current, and the relation is sensitive, it is exponentially related, and it is very hard to fix a current based on a particular value of VE because it is exponentially related. Small change in VB results in a large change in current IC. If you are managed to do so, then you will have a constant current flowing through the capacitor and capacitor voltage rises linearly. If you want to discharge it, either you can go for a switch like this, or you can have a transistor circuit with VCC connected to RC here, properly biased. If you want to make it 0, you can apply high pulse at the base of your transistor. Then it will suddenly comes to VCE sat or ideally 0 volts. So ideally it comes back to 0 practically to a VCE value exponentially. And the transistor should be operating in active region here. Base emitter or emitter base forward biased, base collector or collector base reverse biased, and it is a PNP transistor. An increase in capacitor voltage with respect to ground will increase the potential at collector, this is collector P region. So after some time, this collector base region will be forward biased. So the maximum value of Vc is restricted by the voltage at base Vp. So this voltage should be always less than Vb volts. Otherwise, this PN junction, this is a PNP transistor, PNP transistor. So we should take care about the PN junction, collector base junction that never turns on. So you have a restriction at base. Right, if these current sources are not available, if you want to generate a constant slope SIP circuit, linear SIP circuit, we are going for other technique that is called bootstrapping. Bootstrapping is nothing but you are bringing the effect or change of the circuit, output side of the circuit into the input circuit so that you will make it the charging current to the capacitor is constant due to a change in the output as well as change in the input. The capacitor connected between this node and output node of the circuit is called bootstrapping capacitor. Bootstrapping capacitor. CP. And that will strap your output changes back to the input so that charging current at the input side is constant. IC is constant. Let us see how the bootstrapping techniques works in the given circuit. So initially the switch is at closed position. So voltage across a capacitor Vc is equal to 0 volts and the input to the amplifier is also 0 volts. Voltage gain of the amplifier is A. So output A times Vc of t or A times Vc is the output of your amplifier. I said Vc is 0, that is the input to the amplifier. Then A times Vc also will be 0 when Vc equal to 0, switch is closed. Vout is equal to 0. When Vout equal to 0, if the capacitor Cb is initially uncharged, that will charge to Vcc through the diode. And the capacitor will charge to plus minus Vcc. Right? Through the diode and output side of your amp. Output side of your amplifier. So preferably the output impedance of the amplifier should be low so that capacitor CB, bootstrapping capacitor, able to charge to VCC quickly through diode and output impedance of your amplifier. So preferably low output impedance. Now I am opening the switch, right? So capacitor charges not equal to 0, will have some other value, and A times Vc not equal to 0 will have some other value, and the diode D is biased with a plus Vcc at the anode side, and you are increasing the potential at the output side of your amplifier. Cathode point of the diode Vk will increase beyond this Vcc if output is positive. We are assuming that positive gain of the amplifier, then Vin increases, Vout also increases, Vk goes beyond Vcc greater than Vcc. So the diode D turns off, and the supply voltage VCC is isolated from the circuit. So let us see what will be the charging current flowing through the capacitor IC and what will be the current flowing through the resistance IR. IR can be directly written as IR is equal to voltage at cathode Vk minus this end potential is Vc upon R will give you your IR. Vk is nothing but potential at this point with respect to ground is nothing but plus minus Vcc and plus minus V out. So I will write Vcc plus V out minus Vc upon R. So IR equal to V out is nothing but A times input voltage, that is Vc. So Vcc plus A voltage gain times input voltage Vc minus Vc upon R. Let us see what will be the charging current IC. IC is equal to, you have IR coming from upper branch through R, that is IR, minus you have a branch current here, let us mark it as II, that is flowing into the input side of your amplifier circuit, and I have modeled my input impedance with Ri here. So II will be flowing through your Ri, and there won't be any current into the actual input side of your op amp because the input impedance you modeled here and the current flowing through that is called input current into the amplifier. So II flows through Ri, there is no branch current towards the right side because entire current you have included here. So IR minus II will be your charging current IC. And II is nothing but the current flowing through Ri. Voltage across Ri is nothing but this node voltage, that's equal to Vc, Vc, Vc minus 0 by Ri, that is nothing but Vc by Vc upon Ri. So the current IR was equal to, so IC, IR was equal to VCC plus A times VC minus a VC upon R minus II, that is VC upon Ri. If you are properly selecting the voltage gain, you can ensure that IC is independent of VC. In the expression, it is clear that Vc is a variable, Vc is a variable, Vc is a variable, VCC is constant, R is constant, and Ri is constant. Voltage gain A is also constant. So you have to make your IC independent of VCs. So VC, you have to make all terms related to VC to 0. Then I will have my IC equal to VCC upon R. That's a constant. Implies charging current is always constant, independent of capacitor voltage VC or output voltage A times VC. So you have a VC here and a VC here. So if you are ensuring A equal to a 1 plus term, so we'll have 1 plus VC positive, that is VC positive minus VC will cancel each other. Then this term has to be cancelled. So a positive value of A, one more term here, will cancel the last term. The term should be, A value should be equal to, if that is R upon Ri, you will have your IC is equal to VCC plus A is 1 plus R upon Ri multiplied by VC minus VC upon R minus VC by Ri, right? So if your A is this, I am substituting that value here, 1 into Vc positive, and this will cancel itself. R by Ri by R will be Vc by Ri, R and R will get cancelled. Vc by Ri positive, that will cancel, minus Vc by Ri negative. So effectively your current will be nothing but constant always equal to Vcc by R. So we could manage a current IC flowing through the capacitor when switch is in open position is always equal to VCC by R. And once the switch is in open position, diode D is isolated from the circuit and the charging current is applied by the capacitor CP. Again, if you are closing the switch, output suddenly goes to 0. Since the capacitor CB supplied the charging current for the capacitor, its voltage will decrease slightly from VCC. Even though the capacitor CB is having a large value, the decrease will be negligibly small, even though there will be a slight decrease in potential from VCC across bootstrap capacitor CB. The moment output goes to 0 and this is less than VCC, the diode turns on, acting as a short circuit, and CB is recharged or top up with a voltage VCC again quickly. Diode is on, 0 resistance ideally. Ideally, output impedance of your voltage amplifier is expected as very low, so it will charge quickly. So the purpose of the diode D is nothing but if output is start rising from 0 to positive value, it will reverse bias and VCC is isolated from the circuit. And all controlling is done by the bootstrap capacitor CP. The moment switch is closed, output becomes 0. There will be a slight decrease in voltage across the bootstrap capacitor because that supplies the charging current through the capacitor. So once it is 0, diode again forward biased due to a decrease in voltage from VCC here, that again top up the bootstrap capacitor with a VCC through the diode. And the bootstrap capacitor is always connected from output of your circuit to the point that controls the charging current of the capacitor. So if A equal to 1 plus R upon Ri, you will have a constant slope sweep at the output side out because charging current is 0, so the charging current is constant. That will give you constant going up sweep that is scaled by the gain of the amplifier that produces A times Vc as my output, V out. And if Vc value is nothing but as we discussed, Vc value is nothing but I by C times T, I by C times T, I by C times T is your Vc of T. Here I is VCC by R, so VCC by RC multiplied by T will give you Vc of T in this case, and that is multiplied by A to produce a V out of T, that is nothing but A VCC by RC multiplied by T. So this I am calling it as beta T, so this curve will be beta T, and beta is very greater than IC by C. So that is multiplied by VCC by RC is multiplied by A. That is the gain of your amplifier. So we'll have a scale version of a sweep circuit. The moment you are closing the switch, it will come down. Of course, you can control the switch by using different mechanisms that we'll discuss. Right. So in my actual circuit, I am going to replace the amplifier with an ideal op-amp. And op-amp gain was, amplifier gain was 1 plus R upon Ri. Right, 1 plus R upon Ri. So if you are using an ideal op-amp, the input impedance will be infinity. So R upon infinity, this term, second term will goes to 0. So A will be simplifies to 1. So I have used a buffer amplifier, a unity gain amplifier, negative feedback. If this is VC, my output is also VC because V plus equal to V minus, negative feedback, VC is at V plus, V minus also VC, Vout is also VC. Right, so this circuit is quite simple compared to the earlier circuit. That will work based on the theory what we have discussed. As we discussed, the switch should be initially closed to discharge the capacitor completely. So if you are applying a high pulse here, capacitor is ideally shunted to ground. Practically a VC is set, that's equal to 0.2 volts. So let us assume a VC is set is 0. So capacitor is shunted to ground, shorted to ground. So initial value of VC of T is 0. Right? If you are switching off the transistor, this is acting as an open circuit. And we are ensuring that this RC is extremely large so that the capacitor won't charge through RC, extremely large. So when switch was at short circuit, transistor was on, this VC was equal to 0 and Vout also will be equal to 0. So the capacitor, bootstrap capacitor CB charges from VCC through the output side of your amplifier, and the output impedance is ideally 0 in the case of an ideal op-amp. So CB charges quickly through the diode. On state resistance of the diode is also ideally 0, quickly to VCC plus minus VCC. And the moment I am turning off the transistor, the charging of capacitor through RC is prevented by ensuring a large value for RC. So capacitor charges positively, so this voltage goes up, VC of T, and the unity gain amplifier output also goes up, similar to the potential rise in here. Same rise will be available at output side because gain is equal to 1, unity gain buffer amplifier. So that increase in Vout actually increases the right side plate potential of your capacitor, and this diode is reverse biased because it is going up. This is plus minus VCC. This potential really goes beyond VCC. So VCC is isolated from the circuit, right? So in your capacitor, if you are varying this potential up or down by V volts externally, if this is charged with Q initially, right, with positive Q here, negative Q here. So if you are increasing this potential, the total charge in the capacitor is equal to Q initially. That is nothing but Q equal to CB, C times V. V is nothing but VCC initially. So there is no current flow through the capacitor. So you should ensure the same charge. To ensure the same charge, you should ensure same VCC across the capacitor. So if you are increasing right side plate potential to V, automatically left side plate voltage also will increase to V, same polarity, same direction, so that this voltage is constant equal to initial voltage VCC. If this potential is going up, this is also going up, potential difference will be same, right? So output increases, that forcefully increases this potential, and the potential at upper end of your resistance is nothing but VCC plus V out, right? VCC plus V out. V out is going up as your lower potential, so this is also V out, because unity gain amplifier V out equal to V in, V plus, that's equal to V out now, or VC of T. So V out increases, this is also increases in same manner. So potential difference across R remains at VCC, right? So current is constant, VCC by R, and there is no branch current to the right because ideal op-amp input impedance Ri is infinity. So the current flowing to the capacitor charging current is nothing but VCC upon R. So you'll have a constant slope sweep, linearly varying with time, V out, V T, time interval T, and gain is equal to 1, no scaling between input and output. And since the bootstrap capacitor controls the entire circuit current, there will be a small decay in the potential. Even though the bootstrap capacitance is very large compared to C, slight voltage decay will be there. The moment input to the transistor is high, it acts as a short circuit again. So this will become 0 volts, output also becomes 0 volts. So if this voltage is less than VCC, the diode D turns on and quickly it charges to plus minus VCC. So the top up or recharging of a bootstrap capacitor is achieved by the diode when output is 0. When output is 0 at this instant and before the onset of another sweep. In transistor-based shift generator circuit, similar to last circuit based on a PAMP, we have an amplifier stage here, amplifier stage here. It's a common collector configuration. Its voltage gain is approximately equal to positive 1. The bootstrap capacitor is again connected from output node to the cathode of the diode, and you have R and C, and our interest is to generate a constant charging current IC through the capacitor C. Initially, if the transistor is on by applying a positive pulse at the base of your transistor, capacitor short circuited to ground. That ensures a 0 volts here, and Vout equal to 0. The common collector transistor is in off state because to turn on should have a VBE of at least zero point 0.7 volts. So when VC of T is equal to 0 volts, the transistor turns off and no current flows through the resistor RE. Voltage drop across RE will be 0. That implies output Vout equal to 0. At this condition, when transistor is on, the diode forward biased with a positive VCC here, then the bootstrap capacitor will charge towards plus minus VCC volts from VCC to ground through the output node of your transistor, and this is a common collector configuration. R out is very low, ideally 0, and R in is very high, ideally infinity. R in is ideally very high, infinity. R out is 0, very low. Then if you are turning off the transistor here, switching off the transistor here by ensuring a 0 volts at its base, this acts as an open circuit, so the transistor is isolated from the circuit, capacitor charges, so this voltage rises. Since this is a PN junction diode, output will appear only if Vc of T, or base voltage of your transistor with respect to the ground, increases beyond 0.7 volts. 0.7 volts. So V out will be present and it will be positive when Vc of T crosses greater than 0.7 volts. So I will write this Vc of T as V out plus 0.7 volts. That's why I said voltage gain is not exactly equal to 1, it is slightly less than 1 and approximately equal to 1 due to a voltage drop across the transistor base emitter junction. The moment output increases, this voltage also increases, and this is at VCC. This voltage goes beyond VCC plus V out, cathode of your diode. So diode turns off, reverse bias. So VCC is isolated from the circuit. The entire control is done by the bootstrap capacitor CP. When V out is the output voltage, Vc of T can be written as V out plus 0.7 volts as we discussed. Vb will be greater than VE by 0.7 volts. So the voltage drop across the resistance R will be VR equals VCC plus V out minus V out plus 0.7 volts. That will give you VCC minus 0.7 volts. V out will cancel each other. So the current flowing through the resistance IR will be equal to voltage drop across R is nothing but VR upon R will give you VCC minus 0.7 upon R. Since VCC is much greater than zero point 0.7, VCC will be in the order of 10 volts. So you can neglect your zero point 0.7 compared to VCC. So my IR will be constant, approximately equal to VCC by R. Let us see the value of IC, that is nothing but IR minus the branch current flowing into the base of the transistor. I will mark it as IP. As the input resistance is very large, and usually compared to collector or emitter current, base current IB will be smaller in the order of microamperes, then IC can be approximated as IR itself. So that is nothing but VCC upon R. So your charging current flowing through the capacitor is nothing but VCC upon R. So you're charging a capacitor using a constant current IC. So voltage across the capacitor VC of T will be linearly increasing. Similar to this, you will have your output signal Vout is also linearly increasing because the voltage gain is approximately 1 and it is differs by 0.7 volts. So until VC reaches 0.7, your output will be 0, then it increases linearly, right? So there will be approximately a difference of 0.7 volts at each instant of time compared to your VC of T and V out. Again, if you want to stop the charging of the capacitor, you can stop the transistor by applying a positive pulse. So voltage across the capacitor suddenly drops to 0 ideally. Actually, it drops up to VCE SAT or 0.2 volts. Then if you want to charge the capacitor at the same instant, you can reduce the pulse width on time of your transistor to the same instant it will charge again linearly. Ideally, it will take zero time to come from high VC of T to VCE SAT, but practically it will take some time to reach VCE SAT. So we'll have a linear slope or constant slope sweep waveform at the output side. That's all about transistor based sweep generator. So we have discussed the technique used for bootstrapping, and we have implemented a circuit using an op-amp and a transistor, and we have discussed the working of these two circuits based on the logic derived in the first amplifier circuit. Thank you.